Now we have our first new speaker today, Alex Thomson.
Mm-hmm.
Yeah, and she's from UC Davis.
Yes.
Okay.
Good.
So she's gonna talk about the theory progress in Moiré materials. So yesterday we had experimental progress. This is a theory progress. So let's welcome.
Thanks.
Really?
Am I okay just talking like this?
Yeah.
Okay, cool. I won't try to hold that and write. Yeah, so calling this theory progress is perhaps a little bit I don't think I'm going to be able to cover all of the progress in theory in this 1 hour, but so I'm going to focus mostly on, you know, some of the earlier things in graphene. Yeah, focusing on graphene because that's what Jane was sort of talking about. So I guess you guys probably know that when we take two sort of sheets of graphene and we twist them, we get this sort of moiré pattern that I have shown up here. Of course, the basic band structure just of graphene, graphene's this honeycomb lattice, and you know, we get these Dirac cones. And it's not really that, you know, surprising that when we put them on top of one another and twist, we wind up, you know, getting a different electronic structure than just these Dirac cones that I have here. It's pretty clear. But what's kind of the, you know, I guess, you know, magic observation from 2011, Bitzer McDonald, was that they actually expect there to be this, they expect there to be this magic angle where everything becomes completely flat. And so we can just kind of understand very basically where that magic angle is coming from, you know, from this sort of picture that I have taken, sketched out here. So we can kind of, you know, so if we just sort of draw Dirac cones. So here I'm just reproducing essentially C up here. Well, so these are the two Dirac cones coming from, maybe I should have. So these are the two Dirac cones coming from your top and your bottom layer. They're separated by some amount because, you know, you twist in real space. And so you also have to twist the sort of corresponding boron zones. And so they're going to be separated by some distance in K space, which I'm just going to call K theta, okay? Then, so this is just me separating them. I'm not allowing them to tunnel. When you allow them to tunnel, you kind of, you know, say the tunneling strength is has some magnitude omega or W, then this thing opens up a gap, which will be 2W, okay? And so you can kind of get a very sort of approximate estimate. You can estimate, you know, this magic angle as, you know, when this, you know, this band opening that happens below and above, you know, kind of shrinks down so that, you know, it's completely flat in between. And that's just very sloppy, but this is what you get. And so this becomes, you know, 2W, you know, equals H bar V K theta. So H bar V K theta, that's just coming from the fact that this distance right here is K theta. This distance here is K theta. And if V is the dispersion, then that means that up, you know, here, this is H bar V K theta, okay? And so it turns out that you can write K theta as, you know, 4 pi theta over 3a. And so, you know, you wind up, depending on what the magnitude of, you know, W here, the interlayer tunneling is, you get something that is around, you know, 1.1 here. And so that is essentially the magic angle. This is, of course, not, the good way to do this. There are numerical, models that do this better. One thing that you should note, though, is that essentially theta here, I'm solving for a dimensionless parameter. So it's often, often instead of talking about theta, we talk about this parameter alpha. And so, you can see that once you plug in what, w, v, the velocity, and sort of this is, you can, from that, get the magic angle. And so, my estimate above was really just, alpha equals a half. Okay, so that's just a heuristic way of seeing why you would get this this type of these flat bands. Numerically, what you actually find is that it's around 6.05. So again, it's a slightly lower magic angle. But, we're getting into the territory where this is also, they're so close to one another experimentally. I don't know that people worry too much about getting 1.1 versus 1.05. All right. So, right. So also, if I've just talked about, these Dirac cones that I have, but, in reality, there's a full band structure. I'll talk a little bit more about that. But we can just look at sort of some, estimates based on that band structure. So just using free electrons here, around this magic angle, you have a bandwidth of around 10 MeV. This is, on the higher end for the magic angle from a free electron perspective. And then what you really want to compare that to, the sort of important thing we're talking about, is the interaction strength. So here, it's a Coulomb interaction, and I'm just, again, very roughly estimating that from 1 over r is what the Coulomb interaction goes as. So what is r here? Well, r is going to be the Moiré lattice constant, AM. So that gives us around 15 MeV, which is larger than the bandwidth. So that's telling us that in this model, interactions are essentially on par with the kinetic energy. And I think more than that, you couldn't really say much about what's going to happen, or I don't know that you could trust the predictions. People can say whatever they want, but so that was sort of in 2011. But this essentially motivated the MIT group to make this system so that we could see what happens. And of course, I'm sure you guys all know that the thing that happened was they found superconductivity. And so here, this is plotting the resistance as a function of carrier density and temperature. And so you get these two superconducting domes. Now, and again, and this is close to the magic angle. Now, in that sort of first paper, there's sort of a lot of discussion relating this to sort of Mott physics. So up here at top, I have this sort of canonical cuprate phase diagram, and I have this Hubbard model that people use to describe that. So so in the Hubbard model, you have a electrons just hopping on a lattice in the presence of some interaction strength. And then you dope that, and you get the phenomenology, or presumably you can get the phenomenology of the cuprates. And so, if you kind of look at this type of these phase diagrams, you might think that sort of right here, this is essentially playing the role of, zero doping for the cuprates, okay? And that was sort of what Pablo's group proposed originally. Now, as we will see, it turns out that twisted bilayer graphene and its family of compounds, is sort of a whole family, are different from this Hubbard model in a number of ways. Okay, so that was kind of an introduction. If you guys have questions, please, if you ever have questions, actually just feel free to ask. But what I want to sort of focus on and go into more detail is largely I want to derive sort of the models that people use, to derive those band structures. Because, part of the difficulty here is that we're going to get this continuum model, and it's actually quite complicated and difficult to work with. And so then I'm going to want to talk a little bit about, attempts at simplifying this. There's more complicated models for the cuprates, but then you want to reduce it down to something that is manageable, like the Hubbard model. And that's not going to be nearly as easy in this case. And there's a number of different ways people have sort of looked into doing that. And I probably will not have time to go into very much detail, but I'll try to give some discussion. All right. So, yeah, I'm going to sort of try to derive this continuum model. Again, any questions, please feel free to ask. Okay, so I'm going to start I'm going to do this from a real space perspective, from sort of the elasticity view. First, I first read about it in Leon's paper, which is right here. Okay, so now we know that we're looking at really low energies, really small dopings. So when we want to talk about a model, we only going to need to deal with the low energy parts of the spectrum in graphene. So those are the Dirac cones. So we essentially expand about the K points. We go. Okay. So I've just expanded this operator, so that psi plus and minus are very much more slowly than that exponential that's sort of sitting right out front. Okay. I'm actually going to focus, entirely on the positive K point. Everything. So I'm going to focus entirely on K point. I'm just kind of going to forget about this K minus point. And the reason that is that any sort of tunneling between the two of them would break translation symmetry. So, if you were to have a Hamiltonian and you had something that was like this, that type of term does not preserve momentum. And so it breaks translation. And it's pretty good approximation that this does not happen. We don't need to worry about it. Okay. Okay. So we can write down a whole Hamiltonian for just a single layer. So it's just a Dirac theory. I'm dropping the pluses on the size. And Okay. So this, what I mean is just, sigma x plus sigma y, where these sigmas here are just Pauli matrices that are acting on, the sublattice components of the spinors for the for graphene. Okay, so each of these psi's here is a two-component object, with one component being the A sublattice and the other the B sublattice. So for graphene, just for those that don't know, there's two sublattices, so you need to account for those two both the A and the B parts. Okay, and so now, okay, so this doesn't get us that far. So we haven't gone that far. So what we want to do is we want to focus on perturbations that are weak and slowly varying on the lattice scale. And so what I mean is I want an elastic deformation of this form. So, okay, what does this mean? So big R here, this is a point on the, what I'm going to call undeformed lattice. U here is the displacement field. So, I have in real space, the real position is physical position in real space is little r here. And little r, each little r corresponds to one of the coordinates on our lattice. That's the big R's. And then it is sort of displaced by some little u, which it is convenient to write such that it depends implicitly on little r. Now you can obviously have it depend explicitly on big R. That would kind of make more sense, be easier to think about, but it turns out that it's actually not the most convenient way to discuss this. Okay. And so, even though U of R might be very large, essentially U of R is going to be what accounts for the fact that we're twisting the sample. Even though that could be big, this elastic theory won't really care, provided, delta U is very small. Okay, so provided this U is changing slowly, we should be okay. And so I should say that, yeah. So R is little r is a function of big R, but it's defined, of course, implicitly, from U of little r. Okay. And so that's maybe, so this framework here can work for if you, stretch your graphene number of different things. We're of course interested in mostly in a rigid twist, and particularly a small twist angle. So in that case, I'm going to write R as equal to my twist of z hat cross little r. So this is just, rewrite this like so, okay, so and again, the derivative of this displacement, you can see it is always going to be small because it's just going to be proportional to theta, which I'm assuming is a small number. But obviously R itself might not be small, right? It's not constrained. Okay, so the first thing that we need to do is I need to rewrite all of my, let's just rewrite the Hamiltonian, that Dirac Hamiltonian, in terms of the these new sort of these new coordinates. So we're going to transform Dirac operators and Hamiltonian. So C of R. So you might think that I could just rewrite this, you know, just replace everything. Just, you know, R is now implicitly a function of little r. It turns out that that's not actually, doesn't actually work. You need to add a sort of Jacobian factor here. Out front. And the reason for that is that you want to maintain the canonical commutation relations of the of both of these operators. Okay, so you know we sort of want to have that, you know, this is equal to a delta function. And so the delta function here knows about the coordinates. It's sort of a dimensional quantity. Yeah. That's R vector. Sorry. I'm just proud of myself for putting some notation above. But yeah, thank you. Okay, so that's why we need the determinant. And we can sort of, now we can expand this out. So here I'm approximating the determinant. It sort of becomes a divergence of U, 1 minus the divergence. And we have to account for the fact that, you know, the e to the I big K, you know, it's not big R, it's the difference now, okay? And of course, you know, technically this would also include the other valley, but I don't want to talk about it. So I'm not going to put it out. So this thing here is what I'm going to define as psi of R e to the I big K dot R, which just, you know, implies okay. All right. So next thing we have to do this sort of play the same game with the measure that again picks up the same sort of, you know, determinant factor, which again you can approximate. Oh no, I lied. Like this. And then finally, you also, of course, need to rewrite this, the derivative. Now, yes. What do you mean? I'm changing coordinates. The big K comes from, oh, a big K comes up here. So essentially, if you want to think about it, you could kind of think about it as you do a Fourier, another way of thinking about it is you do a Fourier transform so that you have, like, you know, now I'm in K space. I see if big R is a sum over all momentum. And then you kind of group the Ks that are close to big K, you know, plus positive K and minus K. And you kind of, those are the only things that are going to matter at low energies. I can actually throw everything else out. And then I am just left with, I kind of put everything else into these two objects. It's sort of the fast degree of freedom. No, I mean, I would rewrite this as yeah. But you could also just think about it from this continuum perspective in real space. It's a little. And we'll see a little bit more why it's completely 100% reasonable to not worry. So obviously adding this Moiré lattice is going to break, you know, the underlying translation symmetry of the graphene lattice. You know, it's a much bigger unit cell, which means it's a much smaller symmetry. So we are going to have, you know, different momenta are going to be scattering. It's very, very reasonable to assume that K and K prime do not talk to each other. Unless it's spontaneous, but okay, so where was I? Were you good, everybody, actually? Yes. Yeah. Yeah. That's the physical position in space. You can think about it. We have our lattice, and each point on the lattice is indexed, you could just say, by which sort of number, which carbon atom it is. We're doing everything rigidly, so I don't have to think too hard about it. But yeah, exactly. Good, good. It's going to be a test, so hope everybody's following. Right, we were doing general, I guess, is that what this is called? Okay, so yeah, I'm just trying to reframe my derivative in terms of the little r's, right? And so this is, you know, essentially just plugging in what that little r is. Okay. So obviously this first term is just then acting this on this, just, you know, sets mu equals to nu. So I have d by dr mu. Oh, it's not very good. But then, you know, I actually also have essentially d u of r by big R d by dr nu. Okay, so I don't actually want to have any of the big r's. And so, you know, there's this issue of trying to get rid of all of those little r's. Okay, but, you know, I'm actually doing an expansion in terms of derivatives of little u. And so I could keep sort of iterating this. But, you know, to the order that I'm interested in, it's totally fine to just kind of, you know, say this is r nu. Okay. So that's fine to the level of approximation that we're working in. Okay, okay, so we can just plug this in. So I'm essentially, you know, going back up here to this Dirac equation I had, and now I'm just going to plug, you know, everything in directly. essentially what's going to happen is I pick up, here we get factors. Oh, okay, let's just write it out. Let's just do it. So H Dirac here is d squared, little r now, e to the I k dot u. There's a velocity here. Then I have sigma mu times d by dr mu plus du dr mu d by dr mu. And that's all acting on another k dot u psi of r. Notably, I guess we can see this, these Jacobian factors are gonna cancel out, or sorry, it's these Jacobian factors are canceling out. So yeah, that was kind of, it's good to do it. It's good. All right, so just, yeah. Did I get my, oh, up here you're saying? Yeah. Good. Okay, so we get so this is just rewriting essentially that that part in the middle, if it were to act directly on the psi to the right of it, right? So we're acting kind of this thing directly. Should probably, this thing is acting directly on this, but it also can act on the exponent there. So we have essentially what is a shifts term, which is k dot okay. So this is sort of, so this is a shift of the Dirac point. Now, going back to what I said, like when I started this, when do I have until? 20 minutes? Half hour? Okay, cool. Just making sure. So we can shift this Dirac point. As I was saying earlier, that's what kind of happens when you rotate the, when you rotate, you're also going to rotate the K points. So that's sort of what we have. Now, one thing that's kind of notable is that this is completely independent of any sort of, this is independent of U itself, right? And that was what, that's good because that's the small parameter that I'm I'm expanding it. So, and it's also good because if U is constant, so if the derivative of U vanishes, then my Hamiltonian should not change because you can just move your Hamiltonian and it doesn't matter where your graphene is in the universe. It should still be graphene. Okay, so the energy cannot depend on a uniform displacement. So that's nice. Okay. Okay, so that's one layer. Let's look at multiple layers. Yeah. Let's look at multiple layers and let's have them, twisted. So the inner coordinates, big R1 and 2 are different, but little r is the physical coordinate. So it's an X and Y coordinate. We're not talking about the Z difference, so not an issue. And we're going to have U1 of R be, plus this. And U2 of R minus. So, in total, they are twisted relative to one another by an angle theta, okay? Where theta is small. Okay. So that shift I write is K partial mu U1. Now the K point, we can go back up here. So this K point, I'm done. K point, you guys probably recall, is positioned 4 pi over 3a. So that is the A here is the Bravais-Lattice vector. Sometimes people write A as the intercarbon distance, and they give something slightly different. It's not a big deal, but it's annoying when you're off by a factor of square root 3. Okay, so that's what this is. Right, that's what. So I get this is 4 pi over 3a, and then it's going to be partial mu of u1 of x, because k only has an x component. And so u1 of x is minus y. And so you have to have a delta function, and then it's minus 1/2, 4 pi theta over 3a, okay? And this thing here is precisely what I called k theta before. I just sort of said that's what it is, but now we can see directly from this that this is exactly going to be the shift, because, I mean, I haven't written it out, but k dot partial u, u2, is going to be the same thing, just with, a plus sign. So it's k theta divided by 2. Okay. So, so we can just rewrite, this is just now plugging it in. So I'm going to use a shorthand that is pretty common. So this thing here, this theta sub, the sigma sub theta over 2 is essentially the rotated sigma. So this is just equal to this. The other one looks very similar. Except I put 2's on, this becomes a minus, and this becomes a plus, okay? It means that, so R is X and Y coordinate. So it means that they occupy the same, plane. Yeah. Yeah, I want to know, so I take the 2, I have all of my coordinates, big R1, big R2. That's telling me, I have an index of which carbon atom is which, where it is relative to all the others. But, I want to know where they actually are in physical space. That's what little r is. So I want to write them in terms of the same spatial coordinate, little r. Yeah. Yeah. But you can do any sort of deformation here. It's sort of But yeah. Good. Okay, so yeah, you'll often see this picture of this twisting. Again, this is the K theta that I'm just showing here. It winds up being that this is what gives a what we're going to call the Moiré-Buron zone. That's I'll get to sort of why exactly how we can derive the existence of the Moiré-Buron zone, and that this K theta is actually sort of the edge of that Buron zone. Okay, so I have rewritten these Dirac cones that doesn't really do the job. We need to have them tunneling. So we need tunneling between the layers. So, right, H tunneling. Okay, so this here is a 2x2 matrix that now depends on the difference of U1 and U2. So what we're assuming is obviously a spin-independent tunneling. Kind of actually ignored all of spin degrees of freedom, but this T, as we will see, does have to actually depend on the spinor structure. So that's the sublattice structure of these size. I'm assuming that this tunneling is local. So it's only a function, of R. So, psi 1 and psi 2 are at the same point in space when they're tunneling. Okay. I'm also neglecting any gradient dependence is neglected. Now, okay, so one thing, H channel, depends directly on, U1 minus U2. That is different than the Dirac cone, where it depended on the gradient. So we are actually making an additional kind of assumption here, additional sort of perturbation. I'm assuming here that the sort of twist angle is, partial U is small, slowly varying. I'm also assuming that this tunneling term that I'm adding is also relatively small, okay? Because it doesn't depend on the gradient, so I can't, quite use that argument. I can use that argument, to neglect the gradients of U, and when I'm writing down the tunneling, those things can exist. They can, I don't know how important they wind up being, but there's some discussion of their importance. And of course, it has to depend on their difference. It can't depend on U1 or U2, because then we would be, essentially allowing there to be a constant, when it has to depend on the difference, in order for this to make sense. Now, even if U1 minus U2 is constant, then that actually obviously can change the Hamiltonian, and that's the difference between Bernal bilayer and AA, or any other sort of stacking registry, and those are all have different Hamiltonians that you can write down, and those would sort of, you could account for this in this language, but that would be silly, but you could do it. So, okay. Now here's the big thing. Wow, this takes so long. Okay, there's lots of symmetries. So the biggest one that matters here, or I think one of the bigger ones, is a discrete translation symmetry. So T of U plus A is equal to T of U for A belonging to, the Bravais lattice. So that's the Bravais lattice of the graphene, okay? And that's telling me then that I can rewrite, I can just do a Fourier expansion like this, okay? So that's the big one. So we also have a C3 symmetry. Which probably I'm going to cheat and just copy. Where are we? Go back up where we're supposed to be then. I've been scammed. Okay, so the C3's, sorry. The C3 symmetry, it acts in okay, so there's different ways to represent this. The gauge that I'm choosing here is actually not ideal in a number of ways. And the primary reason it's not ideal is because C3 acts in a weird way. So what we see happening here is that I'm at the K point, okay? Now I have to rotate, when I rotate, I go to sort of this K point at the other corner of the Baron zone. Now, those two operators need to be gauge equivalent, but they don't need to be actually equivalent. And so you need to kind of gauge transform back. You need to sort of shift by Q1 in order to get back there, okay? So, so what we wind up having is Q1 where this is just the rotated and so O3 here is just a rotation matrix implementing. Okay, so everything here, this stuff here is pretty normal. This is normal, okay? This factor here, comes from yeah, it's sort of related. This is related to essentially coming from the K point, and this thing here is coming from having to shift back, okay? So this is kind of annoying, but what is life? Oh, it did. I've been scammed. I've just been scammed. Okay, well, let us. Okay, cool. I have two other symmetries that are important here. One is C2T. So this is an inversion. So you take the position R to minus R, and then you also implement time reversal. Now, why don't I just talk about time reversal? Well, time reversal is obviously going to interchange the valleys, and I only want to talk about a single valley. So, time reversal interchange valleys, but also inversion, which takes K to minus K, also interchange valleys. I put them together and I get this symmetry. Obviously, it is a non-unitary symmetry. And it happens, you can show that it acts in this way on these operators. Second one is reflection, which, about why. And again, you can sort of convince yourself that it should act in this way. Okay, so let's start now. So we start with writing down T of Q equals 0. That's going to be, I think, we can agree, probably the most or at least one of the more relevant, tunneling operators, the sort of constant term. From CT, we get that T is sigma x, whereas Ry, tells us this. Conclude that T naught has to take this form. These are real. Okay. Sort of, but not really. So it's, right. So down here, you can see that, obviously X and Y are different. So, yeah. So you can, with inversion, get, right. So obviously if you do X, that will also take, in this sort of way of writing things, K to K prime. So that's not going to be a symmetry in my single valley theory. But yeah, you could rotate everything. Okay, so now we have TQ equals 0, but the issue here is, of course, that I have this shift. So even though you might say, okay, well, it's Q equals 0, so when I rotate it, it's just going to rotate to itself. Because of the shift, that is not going to be the case in this way of writing things. Now, C3 can write its own sort of set of assumptions. T. So you can derive this, this type of relation. This is the real space, which then translates in, for the Fourier components. To, come on. Okay. The gist of it really is that, what you find is that you need to add two other things, and, you can write down T of U is equal to sum over N equals 0, 1, 2, Q dot N dot U, where this T sub N here is T to the minus Q of N equals W0 plus W1 . And you have to write out the Q's as well. Okay, so here I have Q1 and Q2 that you get written out on this on the board. So, this is essentially like, the answer we wanted, for general U. So, we want to go back now to our rigid twist. So do we have any questions? This was kind of a lot of details. Remember, there's a test. I got a chuckle, so that was good. Okay, so, now we can go back to the rigid twist. U1 minus U2. Okay, And so we have Q dot N dotted with this difference in, that is what is actually, up in here. Remember, I've just been writing Q of U, but it's actually going to be U1 minus U2. So, this is just equal to theta times Qn dot Z hat cross R, which is equal to minus theta Z hat cross Qn dot R. So this here is going to be, this is here the Moiré reciprocal lattice vector, okay? So we have to, essentially we rotate by 90 degrees and multiply by theta. It's really what's happening. And so, again, it's Q1 and so on. Okay, so let's just, H tunneling is then going to be d squared R psi 1 dagger of R times n equals 0, 1, 2. Tn psi 2 plus the Hermitian conjugate. Okay. So together with the Dirac Hamiltonian, this is essentially the continuum model. And at this point, we can see that we have essentially explained why this thing here is the correct Spiron zone, that we want to talk about. Now, you obviously could also have just figured that out by looking at the Moiré lattice that you can see and looked at the what the actual lattice vectors are for that. So that would have totally worked as well. But this way we at least get, along with that result that we kind of could have inferred anyways, we get the, actual structure of this tunneling, which does actually, I don't know, it's not very, the values of Tn are not super intuitive to me, at least. Probably somebody has some cute way to look at it, but fortunately it's not coming from me. Okay, so questions? Cool. So let's go. Yeah, let's cheat. We're cheating now. Okay. Okay, so in reality, what you would do is you'd want to go to momentum space. So, we go to momentum space. K here now takes value in the entire plane. But, this thing here is essentially implementing a shift. So, we have psi 1 of dagger, psi 1 dagger, Tn, and then, it's shifted by that Q. And so if we wanted to do this numerically, we essentially would have a grid and, fold all of these little hexagons on top of one another and calculate their tunneling based on this. And it's not really, there's not really more to it than that. So this is sort of here, that full, that full Hamiltonian. Now I'm only summing in the, I should have said the Moiré-Brouillon zone. And G's here are sort of these Moiré lattice vectors, Moiré reciprocal lattice vectors, okay? And so, plugging this in, you get, well, at sort of 1.1 degrees, you get these extremely flat bands close to charge neutrality with, the appropriate parameters. But, you know, there's a lot of information in this. Essentially, this contains all of the real space, you know, information of the wave functions that you're getting for these states. But, you know, it also has a lot more bands than you want. So technically, it's sort of an infinite number of bands. Now, you would be correct in thinking that you don't need all of those bands. And so how do we, well, how can we sort of move beyond that? I was going to mention there's some other family of systems that Jane talked a little bit about. And so you might say, what about if we could just write down that two-band tight binding model like we had for, so I have 3 minutes left. Oh, it's 1 minute. Can you write down just a Hubbard model? Can you throw out all of this stuff that I was talking about and just replace that with an easy Hubbard model? Well, there's a good indication that that's not going to be something you're going to be able to do. Mostly because, you know, because I have two Dirac cones that remain in the dispersion, you know, that they're separated by this value k theta. Now, those things have the same, you know, chirality because they're both coming from the k valley. So that's not something that happens normally, right? It is not something that happens normally, you know, from a tight binding model description. It kind of, you know, if you could just write down a two-band tight binding model, it would essentially mean you could have, you know, like a local Haldane model, which, you know, it's a topology, which you can't. So that's one way to sort of see that this is an impossibility. And so this thing has what can be termed for fragile topology. So you can't construct, you know, a proper tight binding model, provided we want to keep all of the symmetries preserved. And so one way you can get around that, if you want to keep all of your symmetries, is by looking not at a two-band model, but at some higher number of bands. I think the lowest number of bands you can get is, you know, 5. But here I'm sort of showing, you know, some calculations done by the Katsiris group with 8 bands. And so you can see they're sort of plotting the weight where the wave functions are. And, you know, most of the wave functions are in this sort of set of bands, most of the flat bands, that's the part we want. But yeah, round gamma, you can see that there is sort of these problem regions, you know, where the weight has to be on a different orbital. You can't just put it on, you know, the orbital that most of the band lives in. And so this is already telling us then, you know, this maybe answers at least the question, can this be a Hubbard model? The answer is no. So it actually, there's sort of versions of this continuum model with perfectly flat bands that resemble essentially lowest Landau levels. So, you know, this more sort of quantum Hall ferromagnetism, like you heard about earlier today, type explanation might, you know, be a better sort of paradigm to work from. Okay, and so there's a whole series of strong coupling arguments that you have based on perfectly flat bands that are essentially, you know, the lattice version of a Landau level, of a lowest Landau level. The other thing that they have, another sort of paradigm you can work off from, is this heavy fermion paradigm. So essentially, all of this red region and these sort of here, that would sort of be like a localized F orbital. And then, you know, the stuff at gamma that, you know, you can't put it where you want the rest of the stuff to go. Those are like your dispersive C electrons, you know, from the perspective of a, you know, Kondo lattice model. So I'm sorry I was even a little longer than I thought, but I'm really happy to answer any more questions for rambling stuff. If you guys want. I know you guys want to eat.
Okay.
maybe also talk through this details afterward. Compared to the initial populations.
So ab initio with these unit cells is really hard. These would be essentially like the Kixeris group would be basing these off their ab initio calculations, but it's, I think, I don't know the details of how they do this. It's not, they can't do it, you know, to the same level of precision as you would normally. There's some tricks that they have to use. I am not an expert, but I trust them.
Beyond the band structure, can we predict other things like the correlation rate and higher perspective, like other than this?
Yeah, so the free fermion information, like the actual form of this band structure, in some ways isn't that important. It is like the symmetry relationship and the topology that kind of are the important things. So I'm showing you this sort of, this is done by the ab initio group. They've sort of made this model. And so that works really well. But the model was actually first sort of conceived by Ashwin and Senthal's group. And they just put in random parameters. So like they just tinkered around it till it looks good. And I've actually done like mean field calculations on that model. And you get like the same thing as you do with Hartree-Fock. I mean, with some, you get pretty good. It's surprisingly good. There's some things you can't get, but I don't know. Okay. To the, I don't think I sorry, I don't understand the question.
So just this is the kind of where you have the additional possible
Oh, you're saying, what if I were to include the displacement? So there is I don't know if that's actually what they do, but there's a bit of trickery that comes out here. So when they are AA stacked, they are farther apart. So what you're asking is actually kind of a reasonable thing to talk about. So probably people have looked at relaxation and how that all affects things. What you do in practice is cheat. So the common cheat that you implement is when I wrote down this tight binding model, I didn't really get into the fact that W0 and W1 correspond essentially to AA and AB hopping. So the AA stacking, because they're further apart, and also there's some other, because they're further apart, you can say it's lower than the AB stacking. So that's how you do it in practice. I am also should probably say that there's also strain that means that for any real system, it's going to look crazy. So there's not really that much point in getting everything right, because there's just nothing like, you know, the band structures that you get with strain are all going to be super different. And it's super clear that the phenomenology isn't. So we don't need to worry that much about this, I think. But I don't know. But we need to know about the symmetries. We need to know about like the structure here and sort of how these things behave. But I details. Is the topology is just coming from the fact that I've somehow concocted by this Moiré transformation, this boron zone that has two K values, that has two values of the same chirality, which you can't just do. And that's actually like one of the reasons that all of these Moiré sort of systems are so, they're just so naturally topological, is that this just comes for free. I'm gonna get food.